Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. We have previously established and proved that the optimal cost of sorting is n log n, and there's a link to this video if you wish to review that. So I think it's interesting today to have a look at ways to sort more quickly than that. And I'll show you 3 ways of doing that. They are called counting sort, bucket sort, and radix sort.
We've explained to death and proved and so on that you cannot do better than big O of n log n. So an exciting thing to do now would be to actually do better than n log n. Haha. Clearly, I must be cheating in some way. In which way am I cheating? I'm not cheating, honest, I'm not cheating. I'm simply not working under the assumptions under which we developed the limit that nobody could do better than n log n. And the assumption was that this was a comparison sort, meaning that all I knew about the elements was checking them pairwise and seeing which one was bigger. If I know something else about the elements I'm sorting, I can exploit this extra knowledge some of the time to sort more efficiently. So for example, you're maybe too young to have had that in your home, but when I was little, people had big encyclopedias at home in many volumes. Encyclopedia Britannica in 32 volumes, 32 black volumes. If you come to my office, you'll see a physical instance of that. So it takes space about this long to have all this one. And if you were to do, I don't know, a school project or something, you would take out all these volumes and they would be all spread over the floor, and then you'd have to put them back in order. Would you try and do something like, I don't know, insert sort or bubble sort or merge sort? No, you would just take volume number 3, and you know it begins here, so volume number 3 is going to be about here, and volume number 10 is going to be about here. You would know more or less where they go from the number it is. And so you could actually, if you did that very frequently, you could even mark on the bookshelf itself, that's the place for volume number 1, that's the place for number 2, and you could just look up and put it there. It would have linear cost to put them back on the shelf. So that's such a trivial case that you don't even describe this as a sorting algorithm, of course. But this is to say you don't always have to pay n log n. Now imagine you are an antiquarian bookstore, and so you have many copies of the 32 volumes, many copies of each of the volumes of the encyclopedia, and people come and say, oh, I want a slightly better version of volume number 14, which I already have, but you know some bugs have eaten out a page, and so I want to buy another copy. Okay, right. And the antiquarian bookstore is happy to sell you another copy, and has to find it on this shelf. And so how would you sort this sequence of things where you know it's just going to be volumes from 1 to 32, but you may have many copies of volume number 14. So in the more general case, you are sorting elements from some small alphabet, in this case only the letters A to D, so it's bounded to just 4 items, but there are potentially millions of them. So what you could do is you could go through your input once and check how many you get of each. So let me do this here. So C, I got 1. A, I got 1. C, I got 1. B, I got 1. A, I got 1. C, I got 1. D, I got 1. A, I got 1. B, 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 C, A, C, A. D, A, D, A, and A. So now I know I got 8 A's, 4 B's, 5 C's, 3 D's. If someone said, what's the sorted output? Well, it's very easy. It's A 8 times, then B, 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 B. And then I just read them out from here. I don't even have to look back at those in order to produce the sorted output. And I just paid big O of n. Now, this is if I'm only concerned with outputting the sequence of keys in order. If these things are keys of records with satellite data and I actually want to output the satellite data in order as well, then I have to go back and do another pass to retrieve the right ones to spit out in the correct order. And what would I do then? Well, I would make myself another empty space here where I record where the next one of these should go. So I next of A tells me where I should put the next A I find. I next of B tells me where I should put the next B I find. I next of C, where's the next C? So where should the next A go? Whenever I found an A, the next A should actually go, surprise, surprise, here. Because you start with an A. The next B, well, because I've seen that there were 8 A's, should be in position 8. I have to make space for the A's, and so I have beep, beep. B goes in position 8. Beep, beep. 1, 2, 3, 4, 5, 6, 7, B. Then I have to make space for these 4 B's, and so after that, I can put the C's. So 8 plus 4 makes 12. Plus the 5 C's, the 5 C's go here. Give me this 17. No, that's not what I should write. D, and here I should write 17. And then 3 spaces left for the D's to go here. So having done that, when I find a C over here, I can just do a linear pass over my array and take the first one. It's a C. Where should it go? Where the C pointer tells me, which is where this one tells me. And then I move on. I move this pointer by 1. And I had written a 12 here. No. But I have to erase it and say 13. So as I go on, I have to increment this pointer. That's why it's better to do it with these little sticks in a demonstration like this, or just ignore it and move the pointers around. Anyway, you can see what happens. A goes here, and so the next A should go here, and I would update this value to 1. I find another C, so I stick it here, and the C moves here, and so this one increases by 1. And then the B goes here, and so on. So it's still just a linear pass on my array, so I get 2 rounds of big O of n, which is still big O of n, and I produce the original values with all their satellite data as needed in order in here, and it's a stable sort because I always take them in the order that they came in my input. So that's called counting sort. Counting sort. Another thing I might know about my input in a different situation, I could have, instead of this, oh, and by the way, I should remark that this auxiliary space here is not the same as the auxiliary space we saw for the merge sort. Because what was bad about the auxiliary space for merge sort? What was bad about it? That at least in the way we used merge sort in lectures, which is reasonable and efficient way, the space that I use up is proportional to the input. We managed to do it in half the input. It was still big O of n space that I had to set aside. In this case, this is not big O of n because it's proportional to the size of the alphabet. And I have 4 characters, and I could have 5 million elements in here. So this does not grow with the size of the input. And so as far as the big O notation, this is independent of n, and so it's a constant. So I'm using just constant space, constant, parametric in the size of the alphabet, but it doesn't grow with the size of the string. So it's not so bad. It's nothing to worry about. This is another situation where what I know about the input is that it's uniformly distributed in a finite range. In this case, my range is between 0 and 1. And between 0 and 1, I have some uniformly distributed real numbers, which for reasons of presentation I have limited to 2 decimals, but they could be just arbitrary reals. So if I have this situation, then for sorting them, I can use a simple strategy called bucket sort. I count how many there are, and there are 10, and I subdivide my interval in 10. And I basically stick them in the interval where they should go according to their value. So this one should go here. 1, 2. And sometimes there's more than one that goes in that interval. So I have to make myself some kind of linked list from this position. It cannot just be a pure array. I may have to store more than one. But because I had my hypothesis of them being uniformly distributed, this cannot happen all the time. I'm not going to have all of them in one slot, I hope, although I've not been especially lucky drawing these things at random here. And then what I do is I walk through my slots, my buckets in order, and then I have to do some kind of ordering, maybe insert sort, between the things in the same bucket, and I put them. And it is possible to work out some tedious mathematics that say under these assumptions, then this thing is going to end up linear, despite the fact that I have those small lists, because it's compensated by the fact that it cannot ever hit the decimal case if it was true that they were uniformly distributed. So this is not very frequently used, but may give you an idea of things that you can do in ad hoc situations if you think about the properties of your input. And this other linear sort I'm going to show you comes from way back. So when in the good old times when dinosaurs roamed the earth, and your lecturer was doing his undergraduate course, computing used interesting contraptions called punch cards, which were pieces of card in which you punched holes, where each column was supposed to represent a symbol, and the holes in that column would describe a symbol. So a hole in row 0 would mean 0, a hole in row 1 would mean 1. That's how you encoded the numbers. And if you wanted to encode things that were not numbers, for example, letters of the alphabet, you had a couple of extra rows in here where you could put a kind of shift and say, well, this is shift 1 is A, shift 2 is B, and so on. This is A, B, C, D, and then you continue J, K over here, and so on. As a good computer scientist, you can imagine that if you have here 12 possible rows, then you have an alphabet of 2 to the 12 symbols that you could use. Actually, no, because if you give yourself total freedom about punching every possible hole, you end up with something that looks more like lace than a card, and if you try to insert it into something, it will just tear itself apart. So there was a strict limit on the number of holes you could have in the same column, and this was a small number, I think, not exceeding 3. And anyway, so these things were popular before computers existed, and there existed mechanical devices like this, bigger than this desk, where you could put a pack of cards in one end, and he would do some processing on them. For example, splitting them up by a specific column you would then indicate, and putting them in order. So all the ones that in the column you designate had a 0 would go here, all the ones with a 1 would go here, all the ones with a 2 would go here. And you could then collect the packs sorted by the value they had in the column you had specified. So on the basis of the availability of this primitive, physical availability of this primitive, the algorithm of radix sort was developed. And this is something which is initially very puzzling and confusing, but eventually makes sense. So you have these items which you should consider not simply as 3-digit numbers, but as punched cards, where each digit is a column of the punch card. Or you can you can consider them as things you want to sort, where each column has values in a small finite range, but the combination of all the columns, although it's a finite range, is too big to use the counting sort on. This could be many more than 3 digits, and then you would not be able to do counting sort because you'd have to keep track of too many possible symbols in the alphabet. But it is possible to use a thing like counting sort, or indeed another stable and linear cost sort on the individual items of one column. So we're going to think of counting sort because we just saw a linear cost, but in this case the linear cost sorting was the one provided by the machine. And what we are going to do is to sort the items by the least significant column first. This is strange because you say, well, if I'm going to sort partially by column, I would first sort by most significant digit. And then within the most significant digit, I would sort by next most significant digit. And within that, by next. And that clearly works. But it requires a lot of desk space because you sort them by most significant digit. Then you have to take the pile of the 9s, for example, and sort them by most significant digit. And then within that, you have to make lots of space to keep track of stuff. Whereas here, you don't need to if you sort by least significant digit. So if I had my linear sort that sorted them by least significant digit, what would it give me? Well, the smallest one is this 1. Then after that, what do I have? I have 3. Then I have 4. And this is a stable sort. So I take these 5s in the order they came through in the input. Then the 7s in the order they came through in the input. And then the 9. So if I look at them as 3-digit numbers, this doesn't look anything like sorted. It all goes up and down. But I've sorted the last column. Now next, I sort them by the middle column, ignoring the last column that I already did. So what's the one with the lowest value in the middle column? It's still this one. And then after that comes this one. And then after that comes this 3 and this other 3. And then this 4 and this other 4. This 5, this 7, and this 8. And finally, I sort by the third most significant column, where the smallest one is this one. Have I made a mistake? No. And next comes this. What comes after that? 6, 7, 8, and 9. Well, and as if by magic, now they're actually sorted. Why does this work? It works because I'm exploiting a stable sort. And so when I put into position the things of this column, the things that remain that would be distinguishers besides the most significant column have already been sorted in previous passes, and because the stable sort preserves that order, then they still appear as they should. And so you can actually develop a formal inductive proof that this works, but it does work. It takes a bit of thinking to be convinced about it, first of all, but actually it is a much better idea than going the other way, because you don't need all the extra space that you would need otherwise. So this is a linear sort that you can apply to bounded length strings of symbols, where the symbols come from a small finite alphabet, but the strings themselves, if you consider the strings themselves as symbols, the alphabet would be too big to apply a counting sort to, even though it's a constant, so it is finite. I mean, in terms of complexity, it would be the same. In terms of practical work, you wouldn't be able to use that.